Lab 5 report. Introduction. The purpose of Lab 5 is about creating a computational model that calculates the time taken for a magnet to fall through an aluminum tube and then comparing it to the real-world results. The process used is first conducting trials on dropping a magnet through an aluminum tube, and then the creation of a computational model of the magnet and tube system. Summary results. The experimental average time taken for the magnet to fall through the tube is 1.0254 seconds, while the computational time was a bit less at 0.968 seconds. Introduction. Fundamental principles. The main principles I used were Lenz's law, which states that the direction of an induced current will always oppose the change in magnetic field that produces the current, and the formula for a magnetic field of a dipole at any location, and the derivative of the flux on a single ring. I ran 5 trials for dropping the magnet through the tube, and I recorded the start and end times, and I averaged the differences and got 1.0254 seconds. These were the results of my computational model. It shows the time taken for the magnet to fall through the tube, and the end result once the magnet passed through the tube, and the velocity versus time graph as the magnet fell through the tube. Interpreting the simulation. What color corresponds to clockwise and to counterclockwise, and how do you know? So I think that blue corresponds to counterclockwise while red is to clockwise, and this is because in my simulation, the magnetic dipole moment of the magnet points in the positive y-axis, and so as the magnet falls, a ring below it will feel a change in magnetic field also in the positive y-axis. And because these rings need to create a magnetic field that opposes this change in magnetic flux, it will create, the direction of the current will be clockwise so that its magnetic field will point down to oppose this change. And because my simulation shows this color as red, I think that red is clockwise. So what happens when you flip the magnet? The dynamics of the system basically just flip, and the magnetic flux and the induced current also flip. How does the real-world system compare to the computational model, and how can it be made more accurate? The computational model was a bit faster than the real-world system, and I think the main way that the computational model could be made more accurate is by adding in air resistance. What does the graph tell you about the forces acting on the bar magnet? At a certain point, the graph flattens, which means that the F net at that point is 0 because the magnetic force and the force of gravity have equaled out in that field. Now into the actual code. So I started by initializing all my values for the tube, and then I inputted the mass and magnetic moment specific to my magnet, and this function calculates the magnetic field given a moment and a distance. This function calculates the derivative of the flux given a magnet and ring, and this line calculates the force of gravity on the magnet, and this final line calculates the current on a single ring. This section calculates the magnetic field of the rings and the magnitude of the force on the ring and the magnet. This line calculates the net force on the magnet, and these lines update the bar's position and velocity. In conclusion, this lab allows us to see the effect a magnet can have by passing through a coil, and the computational model gives us a better visual understanding on the strength of the current as the magnet passes through a tube. For the questions, what if the resistivity on the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So the fall time would increase because the current induced by the magnetic flux would increase, and therefore the magnetic force would increase. And since this force opposes the force of gravity, the fall time increases. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Basically, since the geometry is not complete anymore, there are fewer rings and a weaker induced current and dipoles, and so the magnetic force decreases and the fall time decreases too. Thanks for watching.